Hey everyone, this is Colin Speaks. Sorry, I guess about a week or so ago, I learned about something. Actually, I think it was just today on a Facebook post, about something, a theory, which is called the quantum Zeno effect. And here I am, and today I want to talk about it. Maybe some of you guys have heard it, maybe not, and I'll be presenting some of the, and I'll be presenting an example of evidence to support this theory. So let's just jump right into this schlick. Okay? Alright. So the quantum Zeno effect, also known as the Turing paradox, is a situation in which an unstable particle, if observed continuously, will never decay. One can freeze the evolution of the system by measuring it frequently enough in its known initial state. Now, I know this seems ridiculous, but this just interests me, but it seemed quite interesting and very fascinating and something that no one would really expect. And it seems, counterintuitive that by initially observing a particle that you can freeze the particle, it will never decay like an unstable particle. It just seems crazy to me, but let's learn more about it. Let's do a little bit one. Here it says, a laboratory test using atomic physics was carried out by Etano, Heinzen, and collaborators in NIST, Colorado, which I believe that's the National Institute for Science and Technology, at least I believe, who interrogated the atom to see if it has decayed by shining light of a different frequency, which would be excited only if the atom decayed. A follow-up test was carried out by Raisin and collaborators in UT Austin. All of these verified the quantum Zeno effect. So, exactly what is the quantum Zeno effect? Well, we're going to jump around here. It says, sorry, what is it? Well, it's one of the oddest predictions of quantum theory, that a system can't change while you're watching it. And it's been confirmed by an experiment in Cornell, by Cornell physicists. Their work opens the door to a fundamentally new method to control and manipulate the quantum states of atoms, and could lead to new kinds of sensors, which is quite damn interesting. I mean, the more we learn about quantum mechanics in the quantum world, the more I think we seem to be surprised, and the more it just intrigues and boggles the mind. Here it says, the experiments were performed in the ultra-cold lab of Mukund Ventilator, assistant professor of physics, who has established Cornell's first program to study the physics of materials cooled to temperatures as low as 0.00000001 degree above absolute zero. The work is described in the October 2nd issue of the Journal Physical Review Letters. So this is just stating that Cornell, a lab in Cornell, it says graduate students Adelia Schaffer, I don't know if I'm pronouncing this right, Yogesh Patil, and Harry Chuang, pardon me and forgive me if I didn't pronounce it right, work in the ultra-cold lab of Mukund Ventilator, assistant professor of physics. So they're working in a laboratory to view these particles and test this theory. The researchers demonstrated that they were able to suppress quantum tunneling by merely by observing the atoms. This so-called quantum Zeno effect, named for a Greek philosopher, derives from a proposal in 1977 by E.G. George Sudarshan and Baidyanath Misra, again forgive me if I mispronounce them wrong, at the University of Texas Austin, who pointed out that the weird nature of quantum measurements allows, in principle, for a quantum system to be frozen by repeated measurements. I know all this sounds advanced, but you know what? I just find it really interesting, so let's read on a little bit more. And besides, all of these, I will put these links down below in the description so you can check them out for yourself. Physics.org. By their very nature, unstable particles will eventually decay, some faster than others, but according to quantum Zeno paradox, an unstable particle is observed continuously has been said to never decay. Though counterintuitive, of course, you may be thinking just the opposite makes more sense, or the opposite is logical. This effect has been claimed to show up experimentally in numerous ways. Now, in a new study, physicist Peter Toshek at the University of Hamburg in Hamburg, Germany, has argued that most of these experiments do not provide sufficient evidence of the QZP. So this is just one guy who says they fall short, even though there have been experiments in the past. So that just makes you question what you think about this. So again, you can read this for yourself. Let's go here. The official name for them, as you know, is quantum Zeno effect, and it's based off the arrow paradox. And I just thought this was an interesting thing I wanted to share with you guys. Here it is. An arrow flies through the air. It flies in a series of instants. An instant is defined as the shortest measurement of time possible. In any given instant, the arrow has to appear motionless. If it wasn't motionless, there would be two instances, the one in which the arrow was at one position and one in which the arrow was in another position. This presents a problem. There is no other way to define an instant, but if time is made up of a number of instants, and the arrow doesn't move in any of them, the arrow can't move through the air at all. This is just one... I mean, the arrow paradox just blows my mind, in addition to the quantum Zeno effect. So, here, I just presented you guys with this scientific theory, this paradox thing, the quantum Zeno effect, that I just wanted to share with you guys, and the arrow paradox thing, which was very interesting to me. Again, I will put the links down in the description for you guys to check them out yourself. I just thought this was really interesting. And thank you for watching. I will be putting out another Colin Speaks episode later on today before work. So it is Sunday, November 8th, 2015. Thank you very much for watching. Peace, y'all.